Hello, welcome to Learning Unit 10 of G151. And this unit is about the Eutectoid transformation in steel. In the previous learning unit, we learned about three-phase reactions within phase diagrams. And we learned about the eutectic, where a liquid melt would separate into two phases. And we saw how solders solders work, for example. In this chapter, we're going to be talking about a similar transformation of one phase into two to form a finely divided microconstituent, but this time it will be in the solid phase. And that reaction is called the eutectoid. Here we can see the gamma phase splitting up into alpha and beta. And when it does so, it forms a finely divided mixture of alpha and beta. So here we see the phase field for this finely divided mixture, which is called the eutectoid. It's so finely divided, it's considered a microconstituent, almost a phase in itself. But of course, we must remember that, strictly speaking, that microconstituent is composed of two phases, or what would be normally considered phases. Okay, so in order to understand steel, we have to understand the iron-carbon phase diagram. Steel is, of course, iron with some carbon. And in order to understand this phase diagram, there's just a few phases a few phase fields and phase names that we need to be familiar with. So I'm going to go through those one by one so we can become familiar with them, and that will really help us later on. Okay, the first phase that is commonly mentioned when discussing steels is austenite, also known as gamma iron. So austenite and gamma iron are the same thing. It's great that this area has been colored red, because when we normally see austenite in a steel that is not highly alloyed, that the austenite only exists when the steel is red hot. So when you see red hot steel, what you're looking at is austenite. Austenite is iron, the high temperature form of iron that is in the phase-centered cubic crystal structure state. So austenite, gamma iron is the same thing, and they both are iron with a phase-centered cubic structure. Here we see red hot iron. Every time we see red hot iron, you should think, okay, that's in the austenite state. Okay, and when it's in that state, it's soft and malleable, it's not very strong. The carbon content of austenite is up to 2%. It's very important, as that sets the limit of what we consider a steel and what we consider a cast iron. Steels have carbon less than 2%. Cast irons have carbon contents greater than 2%. And austenite is a interstitial solid solution of carbon in iron. Okay, so that's the high temperature form of iron and carbon. So let's cool down here and let's look at this little strip. Okay, this little phase field there is where the ferrite phase exists. Ferrite is almost pure iron. Okay, so ferrite iron, also called alpha iron, they're the same thing. Alpha iron has a very low solubility for carbon, only up to 0.022%. Okay, very small amount. Again, it's an interstitial solid solution, and the reason for this the change is because the ion changes as we lower the temperature from a face-centered cubic structure to a body-centered cubic structure. Excuse me. And so that's what we're seeing here with this crystal structure shown here. So just to recap, austenite is face-centered cubic, high temperature. Low temperature, the ion changes to a body-centered cubic structure, and we call that type of ion ferrite. It has a low solubility for carbon, so the carbon is kicked out. It has to go somewhere. Where does all the carbon that was in the austenite go when the ion turns into the ferrite phase? Well, what happens is that, well, not all of the ion ends up as ferrite. Some of it forms a compound with carbon. And so this is the third important phase in the ion-carbon phase diagram. It's a stoichiometric compound. So the phase field is just a vertical thin line here, shown in red here. It's not really even that thick. I just had to make it thicker so you could see it. So that vertical line is the compound Fe3C, sometimes called iron carbide, but in metallurgy we call that phase cementite. Cementite is a ceramic material. You would not recognize it as a metal. It is hard and brittle. Here we see a polished cross-section of cast iron, and there's a number of phases here, but these white parts here are cementite, extremely hard, extremely brittle areas. So it has a pretty complicated structure there. We must understand that cementite is itself metastable. Okay, so it means that it's not completely stable yet and can break down with further heat treatment into ferrite and graphite. Okay, so the carbon actually comes out as graphite after a prolonged heat treatment. Now, so let's now figure out what happens at this eutectoid that we see in the iron-carbon phase diagram. So here's the austenite phase field. Let's consider I have a iron, okay, or a piece of steel at the eutectoid composition, which is about 0.83%. So let's say here I am, red hot steel. What phase? All of that red hot steel, all of it is a single phase, and that single phase is austenite, gamma iron. Okay, so imagine yourself looking at a piece of red hot steel. That whole thing is phase-centered cubic structure, iron with carbon interstitial, and we call that austenite or gamma iron. Now let's start cooling it down. Imagine it cooling down. Okay, it's still austenite, still austenite. By the way, austenite is not magnetic. So if you put a magnet next to it, it will be very weakly attracted. Okay, so there you go. Non-magnetic iron at high temperature, red hot. Bring it down. We reach this point. Now the carbon has limited solubility below this temperature. The carbon has to basically precipitate out as a different phase, leaving a iron-rich or carbon-depleted, shall we say, or almost pure iron state, the alpha ion. So it wants to split into alpha ion, and then the carbon that cannot fit into the alpha ion must form cementite. Okay, so this single phase gamma is going to split, and when it does, it forms a microconstituent, and that's what this yellow field is here. We also get microconstituent just to the right of it, okay, but for steels, the yellow section is the important part of the phase diagram where the microconstituent is formed. So the microconstituent here is called pearlite. That's the form of microconstituent you get when you cool the steel at a relatively low cooling rate. So this reaction here, the formation or the eutectoid reaction, the formation of this microconstituent of alpha iron and cementite is very important and characterizes steels. And that's why steels can have compositions between 0 to 2% carbon. Okay, that's where this reaction is very important. And then above that we have cast irons. And we're all aware of the fantastic properties of steel. I mean, our whole modern lives depend upon steel, but it's a very modern material, or relatively modern material, should I say, and it's only been around for 150 years. So just to recap, what is often called the pearlite eutectoid reaction happening here. Okay, what goes on there? Austenite turns into alpha ferrite, and cementite. So it splits up into two phases, like oil and water. Yeah, imagine you mix the vinaigrette, it looks uniform, you let it sit, splits up. Okay, but with oil and water, the oil all sits on the top and the water's at the bottom. Not with this. This forms a very finely divided emulsion. Yeah, a bit like milk. Milk is an emulsion. But anyway, that's the limit of that analogy. So this is the pearlite eutectoid reaction occurring right here. What happens there? The austenite, upon cooling, turns into alpha and cementite. Okay, so hopefully this is starting to make some sort of sense. What does pearlite look like, and why is it called pearlite? Here's a micrograph of pearlite, and you can see the white areas are ferrite, the dark areas are cementite. You can see they form lamellae. These are very fine layers, alternating layers of hard ceramic and ductile, soft ferrite. Almost the perfect combination for making a tough, strong material in which dislocations are within the ferrite are blocked by this hard, strong material, and the soft ferrite adds toughness. This means the material is tough, it can absorb energy, and it's strong. It's amazing material, and it's sometimes been called a nanostructured metal ceramic composite. So pearlite is this type of micrograph structure. If we cool pearlite very slowly, you can get a very coarse structure, or not very coarse, but to the point where it starts to diffract light. Those layers, the alternating layers of light and dark, if you polish it, it will cause an interference of light on it, and the surface will start to look pearlescent. Hence the name pearlite. Okay, because the steel has a pearlescent, the polished steel will have a pearlescent look to it. Now, pearlite is strong and tough, but it's not the toughest form of this microconstituent of ferrite and cementite. To that title, or that title is owned by Bainite. Bainite is tougher than Pearlite. So look at Bainite. It looks very fractured and feathery. Basically, it's the Eutectoid, but where the cementite is discontinuous. Okay, it doesn't form these lamellae, these continuous lamellae, which we'll learn later on that we get pearlite colonies, and the crack can propagate all the way around a colony. But we can break up those colonies with these feathery, with a feathery morphology for the cementite, and that's bainite. And that's basically what happens if you allow the transformation into the Eutectoid to occur at lower temperature, where there's not enough time for these beautiful lamellae to form. If you cool red hot iron, which is in a single phase, gamma iron or austenite, if you cool it rapidly, say dunk it into water or oil, there's not enough time for the Eutectoid reaction to occur. And we end up with martensite. Martensite is extremely hard, but it's brittle. So this reaction is very interesting because we can take a piece of steel, and if we want it to be very hard, we could heat it up and just cool it very quickly. There you go. You have a very hard material. And the hardness depends upon its average carbon content. And the carbon content doesn't change. The material doesn't split up, into different regions, because there's no time for that to happen when you quench quickly. We see here that the hardness of the martensite increases up until we get to a weight percent of about 0.6%, and then it plateaus out. Okay, so this is the hardest martensite in the iron carbon phase diagram. So here we go. Let's recap here. There's 4 important phases that we need to know about when we're talking about steels. We have austenite, lives in this region. Okay, red hot iron, single phase. Red hot iron will be single phase, or red hot steel will be in a single austenite phase. And when you cool it down, it's going to want to split up into cementite and alpha iron. When it does that, it forms a microconstituent. Okay, a eutectoid. If we cool this eutectoid slowly, we get pearlite. If you transform at a lower temperature, you can get bainite. If you cool austenite, you just go cool it right down. No time for this eutectoid reaction. It turns into martensite, very hard material. So there we have it. We have an introduction to the phases, the important phases in the iron-carbon phase diagram. Now we've covered some of the main phases within the iron-carbon diagram. Let's go back now and see how is iron produced. So iron occurs in a natural environment as an ore, as iron oxide. One example of iron ore is hematite. So the oxide is reduced using carbon, and the carbon is in the form of coke, which is produced from coal. So we mix the iron ore and the coke together and heat it up in a furnace. Inside, at high temperature, what will happen, there will be a reduction reaction where the carbon will react with the oxygen in the iron oxide, thus reducing the oxide to form iron and carbon dioxide. So if we look at this phase diagram, we can see at the lowest temperature at which the melt will be liquid occurs at carbon compositions of around 4%. This is known as the eutectic composition. The eutectic, because we have a eutectic point right here. Okay? So this is the eutectic composition of iron, and naturally the first melt that's going to come out of your furnace will be the eutectic. When the melt comes out, we can pour it into a mold, which is being done here. And the material we get is not very, it doesn't have great properties. Yeah, it's very brittle. So it has to be further processed. In this state, the iron is called pig iron. Okay, pig iron. For the way in which it looks when it's cast. It looks like piglets suckling off a sow. So for that reason it's called pig iron. So, okay, we can remelt the pig iron and make some cast iron objects. But cast iron, the physical properties of cast iron are inferior to those of, or shall we say, not inferior in every application, but you know, the steel is the. How do we get steel? That's the question. How do we get steel from cast iron? So what we have to do, we have to reduce the carbon composition or content. How do we reduce the carbon content? Well, this is only figured out about 150 years ago. The older processes used air. More modern processes use oxygen. Okay, so you blow oxygen in using a lance. First, you remelt the pig iron in an electric or a gas furnace using very high temperatures, and then we blow in oxygen just above the surface of the melt, and the surface of the melt will be covered with a slag. We blow that in. What's going to happen is that the carbon within the melt will react with the oxygen to form carbon dioxide and will be thus removed, and we can thus reduce the carbon content of the melt to form steel. If you go to a metal yard to buy some, or just to look around, and I will be giving you some extra credit opportunities to do that, you'll see that they'll have many kinds of materials, some based on iron. Those would be ferrous materials, and others not, non-ferrous. So if you do go and look at some steel, you may see some curious numbers, a 4-digit number that somehow relates to the type of steel. And we can understand this 4-digit number. The first two numbers tell you the type of material. So we can look at this table and understand that if you have a 1 up front, it's a plain carbon steel. If you have a 2 at the front, it's a nickel steel. If you have a 3 at the front, a nickel chromium. A 4, a molybdenum, etc. These last two digits give you the carbon content in hundredths of a percent. So, for example, if you have a 1080 steel, the first two digits, 10. We certainly looked at the range here starting with a 1, and we know it's a plain carbon steel with no alloying, no intentional alloying components. 80, the last two digits, give us the carbon percentage in hundredth of a percent. So 80 divided by 100 will give us the carbon percent. So 80 divided by 100 is of course 0.8. So this is the 0.8 plain carbon steel. So 1080 would be. Here's some